Hi everyone, in this video we will discuss process capability, and this time around we will use Minitab. Let's start with the basics. What is process capability? It's a statistical method to evaluate how well a process is meeting customer specifications. In other words, process capability determines if a process can consistently conform to specifications. We'll shortly explore what some of these words mean in the context of process capability. Words like conform, words like specifications. Let's start by discussing the example of a bakery that's producing cookies. The standard cookie size is 3 inches in diameter. And even with machines, it's actually impossible to always have a 3-inch diameter. So what the bakery has done is it's decided an acceptable range for cookie diameters, and the ranges are 2.75 inches to 3.25 inches. So this is what is called a specification limit. Any cookie that's between 2.75 inches to 3.25 inches will be considered conforming. It conforms to the process. It adheres to the specification limits, right? So if you get a cookie that's too small, then you would be unhappy. If you get a very large cookie, as a customer, you wouldn't be unhappy. But as a baker, you'd be giving away too much cookie. Now, let's examine the control chart on the left, and then the histogram on the right. Now, the control chart on the left shows that for the 5 subgroups where data was collected, the process was in statistical control, right? But does that mean that the process was meeting specifications? If you look at the histogram and the circles that I've highlighted, the range of the cookies that it's producing is somewhere between 3.32 inches and 3.42 inches. So you're giving away like a lot of cookie dough for free. And you're basically producing defects. So in the context of Lean Six Sigma process, and especially process capability, defects are any output that falls outside the specification limits. So in this case, the cookie sizes are way bigger than the specifications. Now this is where process capability comes in, because it introduces the element of customer specification. So let's discuss CP, which is also called potential capability. Now, CP can be said to be the ratio of the tolerance to the estimated spread of the process. Why is that? So when you do, say, look at the numerator of this formula here. When you do USL minus LSL, so basically upper specification limit minus lower specification limit, you get what's called allowable process tolerance. So in our cookie example, the allowable process tolerance would be 3.25 minus 2.75. And then we divide this by 6 sigma. Why 6 sigma? Because in a normal distribution, 99.73% of all data points fall within plus and minus 3 standard deviations of the mean. So that's why, so 3 above and 3 below, so you have a total of 6 standard deviations. So by dividing this process tolerance by 6 sigma, we are basically capturing the range of what's acceptable with all the with nearly all of our output, 99.73% of data points. There are 2 assumptions for calculating capability indices. This is for CP and later for all of them, actually, CPK, BPK, which we'll discuss in just a minute. So the 2 assumptions are that the process has to be stable. That's why in the earlier slide we saw control charts. That's how you determine process stability. And then the other requirement is that the subgroup or the sample data has to be normally distributed. Now, capability indices can be calculated for non-normal data as well, or for data that fits a different type of distribution. But that's a separate topic, and I'll probably make another video on this. For this one, let's consider CP and CPK and the other indices which rely on standard normal curve. So now let's discuss what a quote unquote good CP value is and what the limitations of CP as a metric are. Now, the first thing to note here is the CP value and the corresponding sigma levels. Now, I've highlighted this 1.33 here, which corresponds to 4 sigma level. And whether it is in any book or just, as an industry standard, you'll see that this 1.33 has become some kind of a benchmark or a target to achieve, right? Why is that? So let's look at these two histograms here, right? First let's look at why CP is not, or what the limitations of CP are. Both of these processes are actually they're normally distributed, and they are stable as well. They even have a CP of 1. But if you look at process 2, a lot of the data points here are falling outside this spec limit. So this process, even though it has the same CP as this process, it's actually producing defects. The problem with CP, or rather the limitation with CP, is that it does not consider process centering anywhere. So your data could be distributed here, it could be distributed here, as it is the case, and you will still end up getting the same CP. So that's because centering is not included in CP. Now, again, let's understand why 1.33 is considered some kind of an industry benchmark. Now, if your CP, let's say if your CP is exactly 1, right, there would be no room for error. So imagine a curve that goes something like this, and it takes up all this space. So basically it's very tight, meaning that there's no room for error. Even a small shift in your process performance and you start producing defects. What 1.33 does, or anything higher than 1.33, what it does is it gives you this buffer room. 1.33 nicely aligns with 4 sigma as well. So that's why it's become some kind of a rule of thumb, or a good metric to measure your performance against. Now let's discuss CPK. Now CPK includes it's pretty similar to CP, but there's one difference here. The difference is that it uses process centering. So it uses CPL and CPU. The L and the U stand for lower and upper, and it's typically the minimum, whichever is lower ends up being the CPK of the process. So basically, for CPL, you do mu, which is the process mean, minus the lower standard, lower specification limit, and you divide it by 3 sigma. That is 3 times the process deviation. And for CPU, you take the upper specification limit minus the process mean divided by 3 sigma. So again, as with CP, if the CPK is more than 1, it's said that the process is said to be capable. Why? Because it means that the distance, right, from if this is your mean, and any data point, or all the data points are falling somewhere here, then if the CPK is above 1, then all, or nearly all, 99.73 of your output data point will be within those specifications. So if it's more than 1, basically you're within the specification limits. If it's less than 1, if you look at these formulas, if this ratio ends up being less than 1, it means that some of your process data points are outside these specification limits. So anything above 1 is considered a capable process, right? Now let's move on to process performance, PP and PPK, right? Now, as I mentioned here, PPK and PP and PPK, they use the entire data set, all data points to arrive at the overall variation. And that's why PP and PPK are often called the actual performance indices, right? Why is that? Because they capture everything that happened in the data. So if you want to look at this, there is, let's say, these are all the data points. So what CP and CPK will use is the variation within this subgroup. So each day is a subgroup. So you see there are different measurements here: 3.4, 3.3, 3.34, 3.31. What CP and CPK will use is the variation within this subgroup. What PP and PPK will use is that they will take all the data points and they will use the overall variation. And think about it logically, why that would be a good idea. Your customer wouldn't receive cookies from just one day, right? You want to view performance across all days. Customers can get it from this batch, they can get it from this batch, they can get it from this batch, they can get it from a different day. So you want to the customers receive cookies from all batches across all days. So that's why PP and PPK become more robust, because they tell you your actual performance, not just performance within a particular day. So now that we understand these concepts, let's switch to Minitab and let's do our analysis, right? So this is the data from a fictitious pizza chain. There are 20 batches of 5 pizzas each, so there are 100 measurements in total. The data has 2 columns. One is batch, the other is pizza diameter. Basically, we want to see if the pizza sizes are 12 inches or not, and the lower specification limit is 11.5. So if you produce a pizza that's 11.5 inches, that's acceptable. The upper specification limit is 12.5. So if you produce one that's a little bit larger than 12 inches, that's also acceptable. All right. So we mentioned that the data needs to be normally distributed and the process needs to be in control for us to run the capability analysis. So let's start by checking these assumptions. So to do a normality test, you go to stat, basic stats, scroll all the way down to normality test. It's already selected pizza diameter. If you want, you can just delete this and click on this again, right? We leave the checkbox for Anderson-Darling check. That's the most commonly used test for normality, right? And then let's go ahead and click OK. Minitab will generate a graph and will provide us with p-values. Let me drag this down so you can see. So here is our probability plot. As you see, the p-value is 0.858, which means it's higher than 0.05. So we can see that the data is normally distributed. Back in the day, what ASQ used to call a thick pencil test. Just visually, it's also a good idea to look to see how closely clustered these points are to this red line. So basically, can you cover all of these data points with a thick pencil by putting a thick pencil on top of this? I think so, and the data confirms it. So that was the way normality tests were done back in the day, by plotting them and covering it with a thick pencil and doing all these calculations. Thankfully, we now have Minitab. So the next thing we want to check is the process stable? For that, as I mentioned, we'll use a control chart. So we'll go click on stat again and on control charts. And this is the one we'll use, variable chart for subgroups and X bar and R chart. Now you see Minitab has generated a little bit of a description. It says that you use this when the subgroup sizes are 8 or less, which is our scenario. I'll delete this again. All observations of the chart are in one column. Yes, they're in column C2. The subgroup sizes, you can delete this again, are in C1. Now, there's a bunch of things you can check here, but the default option that you get is actually pretty good. So let's press OK and see the chart that's been generated. These are the control charts for sample mean and sample range. All the data points are within the control limits. If any of these was outside the limit, then it would have been highlighted as a red dot. So we see that both for the mean and for the range, the process is stable. There are no red points. So the second condition is also satisfied. Now we can actually run the capability analysis itself. So we go to stat, quality tools, and capability analysis. Now, this capability 6-pack as well, some people prefer this. They would go here and click normal. I prefer, it gives a more consolidated report. I prefer capability analysis. It's pretty good, clean, nice layout. So let's see what will happen when we click on this. So basically, you can select pizza diameter as data are arranged in a single column. The subgroup size is here. The lower spec is 11.5. The upper is not 13, rather it's 12.5. So 11.5 to 12.5 are the specification limits. One thing that we want to do here is there's a metric called CPM. We want to do that, and we want to add 12 as the target there. A perfectly sized pizza would be 12 inches. So you see how it says here add CPM to the table. CPM is nothing but like a CPK with target added to it. Some of these are used by default. Capability stat, CP, parts per million, overall group analysis, and within subgroup analysis. So let's click OK here, and once we click OK, we will be able to see the report. Okay, so here's the full capability report. Let me just zoom a bit so all of it is visible. Now let's break it down. Let's break down this report piece by piece. So let's start with the left hand side here. So these are some of the inputs that we ourselves made. The lower specification limit 11.5 inches. The target is 12. Upper specification limit is 12.5. The sample mean is 11.9944, which is very close to our target of 12. We had 100 observations. Notice the two standard deviations. Overall is at 0.1. Within is at 0.09. So these are all pretty close. Remember, overall includes all the variation. Within captures only variation within each batch. Now let's examine this nice histogram with two fitted curves. So there are two curves here. One is the overall curve and the other is the within curve. So the solid line is overall, this one, the red one here, right? Now you notice the solid line, the one in red here, this is a little bit wider than the overall line. What it means now, if these curves are overlapping, right? Now imagine if the dotted line completely overlapped the red line, that would have meant that there's no batch to batch variation. But the fact that the red line is a little bit wider and the dotted line, which is the within subgroup variation, is a little bit narrower, that means that there is some the batch averages are shifting around. There's some we can spot it in the data as well. Across batches there are some differences, right? Now let's go to the bottom right here, which is the within potential capability. Examine all the numbers: CP, CPL, CP lower, CP upper, and CPK, right? So CP is 1.81. Remember, this ignores centering. But based on CPL and CPK, the minimum of those, the smaller of those values is 1.79. So that's why the CPK is 1.79. So these the CPK is using both the within group standard deviation. It's using the overall standard deviation. So now let's look at the top section here, which is PPK, actual process performance. The PP is 1.66, PPK is 1.65. It's also calculated the lower and upper limits. So as with CPK, so with PPK, the lower one ends up being the process performance. So that's 1.65. The CPM is 1.67. So it's very close to the actual target, which makes sense because if you look at our mean, which is 11.99, it's very close to the target of 12. So if for example, if this process mean shifted a little bit more, then the CPM value would drop noticeably. Lastly, I want to check the ppm total, which is 0.62. That's parts per million. So that what that means is is that we have less than one defect per million pieces. That's actually pretty good, right? So to wrap this up, the overall report, if you view the overall report, the process is quite capable. All the process capability indices are above 1.33. The process is centered near, very near the target. We do see a little bit of a gap between the within and overall capability, which means that there's some room to reduce batch to batch variation even further. But on the whole, the process is performing really well. Hope you found this video useful. Thank you for watching.